Atrial depolarization is transmitted to the ventricular myocardium by the AV node and intraventricular conducting system. The time between the onset of atrial depolarization and the release of depolarizing current into the ventricular myocardium from the terminal branches of the conducting system is represented by the PR interval on the ECG. Dysfunction of the AV node or diffuse damage to components of the ventricular conducting system can result in a delay or even failure of transmission of atrial depolarization into the ventricular muscle mass. This situation is referred to as atrioventricular or AV block. 3 degrees of AV block are recognized. In first degree AV block, all P waves are transmitted to the ventricular muscle mass, and therefore all are followed by a QRS complex. However, the time taken for conduction into the ventricular myocardium is prolonged. First degree AV block is defined by transmission of all P waves to the ventricular myocardium, but with prolongation of the PR interval beyond the upper limit of normal of 0.2 seconds on the ECG. Second degree AV block is defined by failure of conduction of some P waves into the ventricles. As shown here, the periodic failure of transmission of atrial depolarization into the ventricular muscle mass, with consequent absence of an associated QRS complex, creates a visual impression that the QRS complexes occur in clusters or groups. This is what we mean when we use the term group or groupings in this video. There are 2 major subdivisions of second degree AV block, Mobitz type 1 and Mobitz type 2. The distinction is important as they are associated with very different outcomes for the affected patient. Mobitz type 1 second degree AV block is the so-called Wenckebach phenomenon. Looking at this rhythm strip, the QRS complexes appear to occur in groups, and on closer inspection we find that isolated P waves are periodically failing to depolarize the ventricles. With periodic failure of P wave transmission to the ventricular myocardium, this is a case of second degree atrioventricular block. Analyzing the relationship between the P waves and the QRS complexes, we find a progressive prolongation of the PR interval within the group until finally a P wave fails to be transmitted to the ventricular myocardium. This progressive prolongation of the PR interval preceding a non-transmitted P wave is the defining characteristic of Mobitz type 1 second degree AV block. The phenomenon is usually caused by increasing prolongation of the conduction time within the AV node. Mobitz type 1 second degree AV block may occasionally be associated with symptoms, but is considered clinically benign in the sense that it has a low rate of progression to complete AV block. In Mobitz type 2 second degree AV block, again by definition there is an intermittent failure of conduction of P waves to the ventricular myocardium. However, unlike the Wenckebach phenomenon, there is no progressive prolongation of the PR interval before the non-conducted P wave. Analysing this strip, we note that within the groups the PR interval is constant. With intermittent failure of P wave conduction and a constant PR interval, this is Mobitz type 2 second degree AV block. You'll also notice that within each grouping there are 4 P waves, 3 of which are conducted to the ventricular myocardium. This is Mobitz type 2 second degree AV block with a conduction ratio of 4:3. Unlike Mobitz type 1, Mobitz type 2 carries a significant risk of progression to complete AV block and is therefore associated with a significant mortality in the absence of intervention. We should point out that the conduction ratio in second degree AV block, and therefore the size of the groups, varies between patients, and as shown here, may even vary between groups in a single patient. In the presence of very high conduction ratios, differentiating between Mobitz type 1 and type 2 can be a much more challenging task than we've illustrated so far. Making the call matters because the difference in underlying pathophysiology is reflected in a markedly different prognosis for the patient. As shown here, in second degree AV block with high conduction ratios, the groups may be so large that full groupings are not demonstrated on a standard rhythm strip. Furthermore, and more importantly, in the case of Mobitz type 1 with high conduction ratios, after the first few beats, the degree of progression in PR interval length within the main body of the group can be so small as to be imperceptible. The key to making the call between type 1 and type 2 in a case such as this is careful analysis of the PR interval around the time of the non-conducted P wave. In a case of Mobitz type 1, the longest PR interval is seen in the beat immediately preceding the non-conducted P wave, while the shortest PR interval is observed in the beat immediately following the non-conducted P wave. Also, the largest change in the PR interval is observed between the first and second beats following the non-conducted P wave. Despite the apparent uniformity of the PR intervals within the main body of this group, analysis of the PR intervals around the time of the non-conducted P wave indicates that this is a Mobitz type 1 second degree AV block. This situation is termed atypical Mobitz type 1. Just one further point before we move on. Looking at this rhythm strip, you would be forgiven for thinking that we are dealing with a case of second degree AV block. And with a constant PR interval before and after the non-conducted P wave, you may suspect that this is Mobitz type 2. In fact, you will be wrong. This is a non-conducted premature atrial contraction. Ectopic atrial discharges may not be conducted for a variety of reasons, a benign finding on the ECG. Careful analysis demonstrates that the non-conducted P wave is in fact premature, occurring well before the next expected P wave. Also, as expected, the ectopic P wave has a different morphology than those preceding it. Compare this to our case of Mobitz type 2. The P waves occur with monotonous regularity and are of uniform morphology. In addition to the major subdivisions of second degree AV block, two further variants are also recognized. Second degree AV block with a conduction ratio of 2:1 is termed untypable. With only one PR interval before each non-conducted P wave, there is no way of knowing if this is Mobitz type 1 or type 2. This rhythm strip shows another variant of second degree AV block. High-grade second degree AV block exists when at least two consecutive P waves fail to conduct to the ventricular myocardium. In third degree or complete AV block, no P waves are transmitted to the ventricular myocardium. When this problem arises secondary to diffuse damage of the conducting system, a ventricular focus will take over pacemaker function, driving ventricular depolarization. The escape rhythm generated will be broad complex and will vary in rate between 20 and 40 beats per minute. At this stage, you should be able to spot the AV dissociation evidenced by the presence of regularly occurring P waves which show no fixed relationship with the QRS complexes. The distance between P waves and QRS complexes varies continuously, and some P waves are buried in components of the QRS complexes, while others are fused with the T waves. You will also appreciate that if complete AV block arises secondary to localized damage or dysfunction of the AV node, an escape rhythm can arise from a focus within the bundle of His. As depolarization from this focus enters both branches of the bundle of His, the rhythm generated will be narrow complex. However, as the discharges from the bundle of His are not transmitted to the atria, the SA node continues to fire uninfluenced by events below the damaged AV node. Hence, as shown here, the presence of AV dissociation should be detectable. This slide summarizes the material covered in this video. There is disagreement in the literature, particularly with regard to the precise definition of some subtypes of second-degree AV block. We would recommend that you stick with this nomenclature.